Hi guys, I'm Monica. I welcome you all to my channel Aeroker. In this video, we will be discussing a new topic called stream function. In our previous video, we saw about streamline, what is a streamline, and also we derived the equation of streamline. So, with reference to that equation of streamline, we will be deriving a term called stream function. Let us proceed. So let us first consider a two-dimensional steady flow. So we are going to consider a two-dimensional steady flow initially. Now from the equation of streamline, we know what is the equation of streamline. If you would recollect, it is dy by dx is equal to v by u. So in our this derivation, let us put this as equation 1. Now if I say that this u and y are known functions of x and y, if they are known functions of x and y, which means I can integrate them in order to yield an algebraic equation, correct? In order to get an algebraic equation for streamline, I can integrate the above equation. So can I write the algebraic equation in the form like f of xy, that is it is a function of xy equal to c. Let us say this is our equation 2. So now over here, what is this c? C is any arbitrary constant of integration which has different values for different streamlines. Okay. Now what we will do is we will denote this function f. This f we will denote it by the symbol psi bar. Okay, so if I'm denoting this by psi bar, so I can write it as psi bar of x comma y is equal to c. This would be our equation 3. Now this new term which we have introduced, or new variable that we have introduced, new function that we have introduced, psi bar, this psi bar is known as your stream function. Now, what does this equation 3 show? That this is an equation for a streamline is given. How do we obtain the streamline equation? By setting the stream function, that is setting the stream function equal to the constants C1, C2, C3 and so on. While we set this function equal to the constant, we will get the equation of the streamline. Now, there is something wrong or maybe some lapse in this equation, and that lapse is this part, that is the arbitrary constant, correct? Now in order to eliminate this arbitrariness which is there in equation 2 and 3, which is given or which is because of the integration constant c, we will eliminate this arbitrariness. So in order to do that, let us consider two streamlines. So we have these two streamlines considered over here. This is the streamline AB and this is the streamline CD. So now we have considered these streamlines AB and CD in a two-dimensional flow. We will define the numerical value of psi bar such that this term delta psi bar, that is the difference between psi bar equal to C2. One will be C2 and the other one will be C1. So we will have 2. Correct? The difference between these given by delta psi bar would be equal to the mass flow between the two streamlines. So the difference between these two equations or delta psi bar will be equal to the mass flow between the two streamlines. Now, because this mass flow is two-dimensional, that is the flow we are considering over here is two-dimensional. So the mass flow between the two streamlines is defined per unit depth perpendicular to the page. Now, if we consider the mass flow inside the stream tube, so we can consider this as a stream tube, right? Because there's flow going on in between these two streamlines AB and CD. So we can assume that this is our stream tube which is bounded by two streamlines AB and CD, correct? With a rectangular cross-sectional area which is equal to delta n times depth, unit depth, which is perpendicular to the page. So this delta n is the depth between the two stream lines, and we would have our velocity vector in this direction. So now, as you can see from the diagram, what is delta n? Delta n is the normal distance between AB and CD. Normal distance between AB and CD, correct? So now, because we have said that this delta psi would be the mass flow between the two streamlines, so delta psi over here is nothing but the difference between two streamlines, correct? C2 minus C1, we can write it this way. Let us take this as our equation 4. Now, does this eliminate the arbitrariness completely? For instance, maybe we have the value of C2 and C1 as well. But are there some questions still arising over here? Is the arbitrariness completely removed? Yes or no? We reach to this question, right? So the answer is, it does not remove the arbitrariness completely, but it is making things a little precise, because previously we did not know. We knew that the function is just equal to C. Now we are making it a little precise by defining it between two streamlines and having the value of the streamlines, or having the streamline equation, correct? So now, for example, what we will do over here is, we will consider a two-dimensional field and choose any one of these arbitrary line and give it a value psi bar is equal to C1. So for our convenience, what we do is, we choose this lower streamline as psi bar is equal to C1 and psi bar is equal to C2. So now we have decided which is C1 and which is C2, correct? Now what is the next task that we can do? Let us have a look. But before that, we have some points to be discussed. So what are those points? Let us have a look. Now, because we have chosen this C1 and C2, for example, if I am choosing, as we have chosen over here, the bottom line to be psi bar is equal to C1, so certainly the other would be C2 by definition, correct? Now, when we choose this streamline to be defined, which one would be C1 and which one would be C2, the value of this C1, it usually depends on the geometry of the flow field. These values depend on the geometry of the flow field. Kindly keep this in mind. Okay. Now, in case I say that the type of flow which we are having over here in the stream tube is a steady flow. So what happens in case of a steady flow? Whatever mass flow is inside the stream tube which is going, it would be constant throughout the stream tube. Now, what I say is, this C1, when I am considering, I say that psi bar 1 is equal to C1, that is the bottom line of the stream tube. When I say that psi bar 1 or psi 1 bar is equal to C1, which means I can write psi 2 bar as something of this sort, which would be equal to C2, and that would be equal to C1 plus delta psi. If we develop the derivatives of psi, if I'm going to develop the derivatives of psi, what would it give me? We will be able to find the flow field velocities. In order to obtain this relationship, we are going to make some considerations, some assumptions. What are those considerations? Let us have a look. So, first consideration what we make is the same, that is our streamlines AB and CD. Now here the assumption that we are going to take is that the streamlines are very closer to each other, that is delta n is small and the flow velocity V is constant across delta n. So when the mass is flowing through the stream tube per unit depth of a page, can I write delta psi in the mathematical denotation as rho V delta n? Correct? Because it is per unit depth. You get it? This is the basic mass flow formula which all of you might have gone through. In another form, if I get delta n on this side, I can write it mathematically in this form as well. Let us say this is our equation 2. Now, what if this equation, in this equation, oh, I beg my pardon, it is equation 5. Yes, in this equation 5, if delta n tends to 0, what happens to the equation? How can I write that? Can we write it in this form? Rho v limit delta n tends to 0, delta psi by delta n, which is equivalent to dou psi upon dou n. Correct? What does this equation 6 depict? What does it say? That in case we know the value of psi bar, then we can obtain the product rho v by differentiating in the normal direction. If we differentiate, if we know the value of this term, this particular term psi bar, upon differentiation in the normal direction, we get the value of rho v. Correct? But this seems a little bit difficult to obtain, right? Mathematically, little complicated, where to go, how to solve. So in order to ease our problem, what we are going to do is, we will obtain the practical form of this equation 6 by considering a Cartesian coordinate system. How do we consider that? Let us have a look. Consider the same streamlines AB and CD. So this is our Cartesian coordinate system. This is your X and this is our Y. Now this is the velocity vector. This is psi bar. And let us say over here we have psi bar plus delta psi bar. Now you see a dotted line over here. What does that depict? Let us see. So in this figure, you can see that the normal distance delta n is equivalent to the force that is moving upward in the y direction. This delta n is moving in the y direction by amount delta y. Correct? So this delta n spreads into moving upwards in delta y. And then we also have in the negative direction of x, that is delta x, that it is moving in the left in the negative x direction by the amount delta x. Also we have components of velocity forming over here, that would be u and v. Now due to conservation of mass through delta n per unit depth, we have conservation of mass over here. What happens to mass flow through delta y and delta x? Or what happens to the total mass flow? It is equal to the sum of these two directions, that is mass flow through delta y and mass flow through negative x. Total mass flow gives me that. So can I write total mass flow is nothing but my delta psi bar, which is given by rho v delta n. So how can I write rho v delta n now? Rho v delta y plus rho v into minus delta x. Correct? Let us say this is our equation 7. Now, the same assumption which we considered previously, that is CD is approaching AB, that is both the streamlines are getting closer, and when I say that, I will apply my limit, and when I do that, my equation reduces to this form, that is rho u dy minus rho v dx. Now we know that psi bar is a function of x and y, correct? So if we apply chain rule, or if we use the chain rule, so when we use this chain rule and if you compare these two equations, that is equation 8 and 9, can I write as rho u is equal to dou psi bar by dou y and rho v is equal to dou psi bar by dou x? Is there something missing in the equation? Yes, certainly we get a negative sign over here. Upon comparing these two equations, we get these two equations. Let this be 10a and 10b. What are these two equations that we have obtained over here? Yes. So the equations are, as we said, that psi is a function of x and y, and it is known to give the flow field. Then at any point in the flow, what happens? These rho u and rho v can be obtained by differentiating psi in that respective direction. Correct? In this equation, we are able to see that, which means I can obtain the velocities by using this equation. Now this was in the form of Cartesian coordinate system. What if I want to write the same thing in polar coordinate system? So in polar coordinate system, you get the equation in this form. The derivation process is the same. You can apply the polar coordinate system and derive it. I leave it up to you as a homework of this video. Let us name this as 11a and 11b. Now, what are the units of psi? That is our stream function. The SI units of psi is kg per second meter. This stream function psi is defined for both types of flows, that is compressible as well as incompressible flows. In that, initially what we are going to do is we are going to consider incompressible flows, and when I say my flow is incompressible, what happens to these equations? Let us have a look. Now when I say my flow is incompressible, which means the immediate point that comes to your mind is density would be constant, which means what will happen to equation 5 that we have derived? That is this is our equation 5, or maybe you can consider equation 6 as well over here. If I substitute in this equation, density is equal to constant, I am left with V is equal to dou psi by dou n. Correct? This is what happens when I say my flow is compressible. Coming back to our equations 10a and 10b. What would happen if I say density is constant in this case? We would be only left with u and v. U would be dou psi by dou y and v would be minus dou psi by dou x. Let us say this is our 12a and 12b. Similarly, if we apply the same concept to these two, 11a and 11b, what we are left with? We are 1 by r dou psi bar by dou theta, and v theta is equal to minus dou psi bar by dou r. Correct? Let us say this is our 13a and 13b. B. Now, as you observe these equations for compressible and incompressible flows, the characteristics that the incompressible equations possess are almost analogous to the compressible ones. Correct? Now, what we are going to do over here is, there is one difference that you might have spotted over here. There is one thing missing in this equation and I have written it over here. If that mistake has caught your eye, then yes, here you are not going to get psi bar in the terms of incompressible flow. That is, for an incompressible flow, what we are going to do is, we are going to denote our stream function just by psi, whereas for compressible flow, we denote it as psi bar. Correct? So now when I say for a compressible flow, psi bar x is a function of x comma y equal to constant. It is the equation of streamline. Now when I say rho is constant, how can I write? Can I write psi of x comma y is equivalent to psi bar by rho? Yes, we can write psi in this form, correct? So which means constant is also the, that is, this part is also the equation of a streamline. This is the equation of streamline for incompressible flow. So now one term we said over here is that delta psi bar is the mass flow between the two streamlines per unit depth. And what is rho? Rho is mass per unit volume. So then physically what happens if I write delta psi, that was for incompressible flow, then it would be delta psi bar by rho, right? What would this represent? This represents the volume flow per unit depth between the two streamlines. What is the unit of delta psi? Unit of delta psi can be written as meter cube per second, which is nothing but the volume flow between the two streamlines. So what is this concept of stream function? We saw psi bar as a stream function for compressible flow. Then we saw psi as a function, stream function for incompressible flow. One thing we could understand from the equations is that we can get velocity. If we know the value of psi, we can get the velocity in that particular direction. U is in x direction, v is in y direction. What are the conclusions that we can make up from this derivation? Let us have a look. Now this term stream function or concept of stream function, it is a very powerful tool for two reasons. What are those two reasons? Let us have a look. And here we are going to assume that we know psi bar or psi, either compressible or incompressible flow. We know the values or the functions, that is psi bar of x comma y or psi of x comma y, are known throughout the 2D field. If I know them, then psi bar is equal to constant or psi is equal to constant will give me the equation of a streamline. That is the first advantage of defining this term stream function. Correct? What would be the second advantage, as we discussed just now? That is, the flow velocity can be obtained by differentiating this term psi bar or psi with respect to that particular direction. Yes? So these are the key points that we come to know after the derivation of stream function. We will discuss more about this stream function as we proceed in our journey of aerodynamics. You will find it very much interesting that we had studied it there, and when you will go back to that concept, you will come to know. Thank you for listening. Stay tuned.